Here today we have Florian Hann from Fraunhofer, and he will be talking about the mine thermal energy storage in the Ruhr area in Germany. Hi, Florian.
Hi, everyone. Welcome from my side. I'm working at the Fraunhofer IEG, and together with my colleague René Verhoeven, I'm leading the working group post-mining exploitation. And today I will give you an update about two of our MTES systems that we are currently working on in Bochum. On the front page, you can see a nice picture of the visitation mine, which is close by to our site, and it depicts like a small scale operation from the 50s. And we drilled into a similar small scale mine at our site, and that's something I will talk about in the first part of the presentation. But first, let's continue with our motivation for the projects. And just a second here. And that comes to the bathtub challenge. If we look at our energy demand, we can see that over 50% of our energy is utilized for heating and cooling purposes. And if we look at the renewable energy portions, that we see that there's still a lot to increase that part. And that is majorly due to the fact that we have a mismatch between supply and demand of renewable energies, for example, solar thermal power. And to overcome this mismatch, we need storage capacities. For instance, we can utilize ATES systems, which is very well known in the Netherlands. There's over 2,000 systems for low temperature ATES systems. You can also implement MTES systems, which is widely implemented in Denmark, or also think about borehole thermal energy storage. But especially in the Ruhr area, we thought about reutilization of the mining infrastructures for mine thermal energy storage systems. And that's something I would like to bring to attention in the further presentation. Because in the end, we have to answer the question of how are we going to meet the heating demand in the future with a distinct seasonal profile without fossil fuels, but with the same security of supply. For this, I would like to present the heat store project and the follow-up project Winzer, which we implemented in Bochum. And during the heat store project, we drilled into an abandoned coal mine at the premises of the IEG. You can see here, this is our drill site. We drilled 3 wells into the abandoned coal mine. And 2 of those wells, the MP1 well and MO1 well, are utilized at a depth of 64 meters for a heat storage pilot site. We also connected those wells with a small district heating grid and also implemented a concentrated solar power plant as a renewable energy source. From the Water Authority, we have the right to heat up the mine water from 11 degrees up to 60 degrees. And that's the maximum storage temperature that we can apply at our site. So these are the 2 wells that we're using for our test operation. Here you can see the completion and also the stratigraphy of our wells. On the left-hand side is the production well, the MP1 well. We have a 4-inch pump installed at 31 meters. Mine water is pumped from the drift, heated up to 60 degrees, and then re-injected into the second well, the MO1 well. We have PVC casings installed with a diameter of 195 millimeters. In the drift or in the mine layout, they have a filter screen with a mesh size of 3 millimeters. So, and those 2 wells are 50 meters apart, and we're circulating the mine water, the heated up mine water in that part of the 4th level of the mine layout. Here are some recent data from our heat injection tests. So these are surface temperatures. We're not only using a concentrated solar power plant at the moment for heating up the mine water, but also an air source heat pump that has a power output of 65 to 70 kilowatt. And with that, we can heat up the mine water roughly around 40 degrees Celsius. We also have some peaks where we have the CSP included. We can also see the temperature increase in the inflow part of the mine. Currently, we're operating the system with a flow rate between 3 and 5 cubic meters an hour, and we have an average output, thermal output of, as I already mentioned, between 65 and 70 kilowatt. But we also have some peaks if we also include the concentrated solar power plant. And we can also see the accumulated stored energy that we had till the end of May. It was already almost 100 megawatt hours stored into the mine. We also have DTS cables installed in our wells, and this gives us a nice vertical profile of the heat injection over time. We can also see that we have some parts where we had downtime, maintenance parts, and also some parts where we had, more or less based also on vacation times, where we had to shut down the plant. We can also see some fluctuating parts that is more indicated that the concentrated solar power plant is in operation. And then the next slide, you can also see from the production well that we also in May had a thermal breakthrough of the temperatures. So that is indicated around here. So in the end, if you have a look at the subsurface temperatures at the casing shoe, we can see that the temperatures inside the mine increased to a maximum of 27.5 degrees, and that we could also see in the production well that we also went up to 17.5 degrees. Currently, we're in the execution of a production test, and hopefully by the next symposium, I can show you some results on the efficiency of the storage. So this is a short update on our existing MTES system. And I would like to continue with a second MTES project that we're concluding in the PUSH-IT project. This is an European project that we're started in 2023. We have 3 demo sites that focus on ATES, BTES, and MTES, and we also have 3 demos follower sites that also try to implement our lessons learned from the demo sites. So in Delft, there's an ATES system. In Darmstadt, there is a BTES system, and in Bochum, we are implementing a second MTES system at the site of the Ruhr University. Here's an overview of the already existing small colliery that we implemented the MTES during the Heatsoar and Winzer project. And the second MTES system is going to be erected at the technical quarter of the Ruhr University. Here is the center of the heating and cooling grid of the southern part of Bochum. And below that technical center, there's the first drift of the Mansfeld colliery that we drilled into already. And that drift was also utilized as an underground bunker during the Second World War. So the original volume of that drift is around 10,000 cubic meters. So that's a much larger storage area than we already have from our previous MTES system at our site. What is important for a storage system is that we have an isolated part of the mine that is not connected to other parts of the central dewatering station in Bochum. And here we can see on the vertical layout that we don't have any connections to other mine layouts that are connected to the dewatering system. So that is very important to highlight. At the site, we have a heating and cooling grid, and the thermal power for the heating grid is around 100 megawatt. And for cooling, it's 10 megawatt. The heating grid is fed by CHP plant, and also in the wintertime, it's supported by 3 additional gas-fired boilers. The cooling grid is operated by 3 turbo chillers. And in addition, since 2021, we also have a data center that could utilize surplus heat during the summer. So in summary, we have the potential of 3 to 5 megawatt of surplus heat. So this is a very high potential on that side to be utilized in a storage system in the future. So here are some pictures from the preparation of the drill site and the drilling of the first well. So we had to create the drill pad. We have the transportation of the mud unit and also the drilling rig. Here on the right-hand side, you can already see the drilling rig in operation for the drilling of the first well. And we also have some pictures here of cutting samples every 1 meter. So at the end of last year, we finished also the second well. We can also see that for the casing, we utilized a GRE casing from Heusmann with a diameter of 9 5/8 inch. The drilling diameter is 12 3/4, which is slightly bigger than from the previous project. And we could successfully drill into the mine void and also install the GRE casing down to the depth of 120 meters. And here you can also see a deviation log, and we only had a deviation of less than 1 meter from the starting to the target point, which was very nice. And here on the right-hand side, you can also see camera run from the second well that we could confirm the mine void. And here's some overview of the installation of the filter wrap filter tube. We also installed a DTS cable. Here on the second picture is a connection to the GRE casing. For cementing the annulus, we installed first a packer and then cemented up to the surface. And then for the further installation, we utilized centralizers, and you can also see the cementing pipes for the cementing of the annulus to the surface. And the last work that we did in February currently was to start the mine water sampling at a depth of around 120 meters. We had temperatures between around 11 degrees. The electrical conductivity was not very high, so a little bit slightly above drinking water. pH is neutral. The oxygen level was quite high because it also has some near surface influence. And we also have some short video on the sampling process. So first, removing borehole cover, most important. Taking it off, preparing water sampler. Yeah, so I get already past the 10 minutes. So I will stop the video here and just close off the presentation with an overview of the mine layout that we digitized in the southern part of Bochum. We focused on 2 MTES systems, but the bigger mine water scheme is going to be implemented at the end of this year at the Dunbaum colliery. That's probably part of a further talk for next year. So with this, I would like to thank you for your attention. Glück auf.